Okay, hello everyone. Uh, in this lecture, let me see. I guess we need to refresh our memory with the things that we have learned the last week. So I guess we should go back to this slide and review what we had learned. So qualitatively, we have learned and reviewed PNP BJT operation. So the basic idea was when the BJT PNP BJT was working, the emitter junction, collector junction should be forward biased and reverse biased respectively. Again, the emitter junction means uh, the junction between emitter and base. That emitter junction should be forward biased. Then the role of emitter was what? Yeah, to shoot out many holes into the base, right? So the emitter junction should be forward biased, and emitter can significantly injecting its own holes into the base. How about the collector junction? Yeah, collector junction should be reverse biased. Then um, the injected holes from emitters throughout the base can be well arrived into the collector region. So the role of collector is to get and collect many holes coming from base and emitter. Okay, so in summary, the working principle of BJT can be understood with a forward biased emitter junction and reverse biased collector junction. So this working operation can be denoted as active mode. Again, the BJT is working in active mode. When the emitter junction is forward biased, the collector junction is reverse biased. Okay, so last lecture we have reviewed uh, each current component from emitter to base, from base to emitter, from base to collector, and from collector to base, even from emitter to collector. So we have obtained the current gain beta DC IC over IB. So with that in mind, in today's lecture, we would like to come up with the BJT device design guideline. What is the best option, best menu to have the best performance BJT device? Okay, so what is the solution? I guess you should have your own time and think about and write down one or two sentences how to boost up the BJT's performance. For example, the doping concentration emitter should be higher than the doping concentration in collector region. True or false? In terms of BJT performance. How about the base current? What if the emitter junction is not forward biased but reverse biased? Then what would be happened? Is that good or bad in terms of BJT performance? Even if the performance has been worse, any other application for us to use it? Any tiny room for taking advantage of using the, ugly biased BJT device? Any other option? So please have your own time, take your time, and think about how to design the BJT device to achieve best performance. Okay, so please stop there here and take your own time. Okay, but to make our life much easier, I'm going to begin the basic guideline of BJT device. So herein you can see that to achieve what? Yes, high current gain. So since BJT has been well used and adopted as a uh, amplifier in analog integrated circuit, so BJT's performance has been evaluated with its own current gain. Okay, so in case of common base, I guess a common base, yeah. No, common emitter. We're gonna learn that common collector, common emitter, common base. There are actually three different configurations in building up the BJT based integrated circuit block. So we're gonna learn that, but mm, just just memorize. Common emitter case, the gain can be evaluated with beta. Okay, so beta DC is input output. Okay, so in this case, the input current is a base current and the output current is a collector current. Okay, so common emitter case. Okay, I guess you're very familiar with Mosfet instead of BJT, so you may remember this kind of circuit configuration. So V in, that is V out, and that is load register. And this MOSFET M1, so this source has been grounded. That means a common source circuit amplifier, MOSFET based amplifier. So since in my lecture I'm using a kind of P-type MOSFET, right? That is corresponding to the PNP BJT, right? So in case of PNP BJT case, a common source is corresponding to common emitter. Okay, so in that sense, the emitter electrode has been grounded and used as a common electrode. And if you're not still familiar with what I have just said, that's okay. We're gonna learn it, the BJT circuit configuration, sooner or later. Anyhow, here the DC, the current gain for common emitter BJT amplifier can be observed and evaluated with this with the ratio of collector current to base current. All right, the question is how to achieve very high current gain. I'm talking about this beta value. How to achieve a high current gain? That means we need to increase collector current as much as high as possible, okay, for the given base current. Definitely, since this BJT is working in active mode, I mean the emitter junction is forward biased, collector junction is reverse biased. And how to collect or how to boost up the collector current as high as possible? How to do that? Yeah, this IC, collector current. Let's go back to this slide again. The collector current, this, and that. How to how to have the collector current being high and high? Yes, you should increase the total amount of injected holes coming from emitter. So the answer can be found here. How to boost up, how to increase the total amount of injected holes from emitter to base. How to do that? Yeah, in PN junction diode, we have learned it. If P side is very heavily doped and N side is relatively lower doped, I mean the one-sided PN junction diode, then all the injection of carriers can be governed by heavily doped part. So in this, say P plus N minus junction, then most of the injected carriers originated from the holes in the P plus side, okay? Because it contains humongous number of holes because it is heavily doped, okay? So as described here, the injected minority carriers holes from emitters, P plus emitter, right? Should be injected as much as possible. And the next job for those injected holes in the base regime is not to be recombined with electrons in base. Going back to this slide again, we did our best to inject many holes into the base. Why? because these all the holes should be well arrived into the collector. Otherwise, we cannot achieve our goal. The goal was what? Yes, to increase collector current IC, right? Then the holes, the injected holes into the base regime should be well survived. Why? Why survived? This is anti-Brizon. So many electrons are available so that the injected holes from the emitter should not recombine with electrons in the base regime and should go into the collector region. Okay, so in that sense, we should increase the total amount of holes, I mean the minority carriers in the base regime should be injected as much as possible. For that purpose, we should increase the doping concentration of emitter. That would be good idea. I mean, the one-sided PN junction is necessary in emitter and base junction. But that's not enough. Since base regime is anti-material, so the injected holes would be recombined too much with the majority carriers, which is electron in anti-region. So we should avoid the recombination events as much as possible. How to do that? Yes, we should make the base regime very narrow, very small. So going back to this cross-sectional view again, once suppose that many holes has been well injected into the base regime, and since this length, the width of base is very narrow. How narrow? We have learned the basics. Did you remember this? L sub P, holes diffusion length. You know the physical meaning of this? Yes, the average distance that the minority carriers can survive in the sea of majority carriers. So this LP is a kind of a good indicator how to design, how small, how narrow the base regime is in the PNP BJT. So if this width of base is much narrow than the diffusion length of minority carrier, then on average, many holes cannot be recombined with electrons in the base and can be well arrived into the collector region. That's what we want, right? So here in injected minority carriers should not recombine within the quasi-neutral base regime. Okay, so for that purpose, quasi-neutral base region should be much shorter or narrower than what? Than the minority carrier diffusion length in base, right? Then the goal we are looking for, or we would like to have, can be well satisfied. Okay, so in summary, the P plus N emitter junction should be forward biased definitely. Then we are ready to inject many holes into the base, but that's not enough. We should make the base region, I mean the quasi-neutral base region, other than the depletion layer. Okay, so you should remove the depletion. Do not take into account the depletion layer width when you are thinking about the base regime. So in this sense, I have used the quasi-neutral base regime. So in the quasi-neutral base regime, the injected holes from the emitter should not be recombined with electrons in the base region. So for that purpose, the base regimes, the total length of the base quasi-neutral base regime should be much shorter than the minority carrier's diffusion length in the base. Okay, so this is the very first device design guideline when it comes to the BJT device. Okay, so if you have any chance to design the BJT device, say in 22 nanometer CMOS technology platform, for the analog circuit designer, you should provide the option of BJT device. Then the first one is the total width of the quasi-neutral base regime should be much narrower than the minority carrier's diffusion length. Usually, depending on the doping concentration, but minority carrier diffusion length is in a scale of a few 1/10 of micrometer and shorter. So just say 100 nanometer or tens of nanometer. Okay, so please have your own number when you have a chance to design a BJT design device. Okay. All right, now let's move on to the next one. That was first device design guideline. Second one is let's read out it. The emitter junction, I mean the PN junction between emitter and base. The emitter junction current is comprised of what? Comprised almost entirely of carriers injected into the base. So I'm talking about this. Yeah, this part. Most of the uh, the emitter junction current. So how much current? Emitter current means, this and that. Those two components consist of emitter current. So herein, the emitter junction current is comprised almost entirely of carriers into the base rather than carriers injected into the emitter. In other words, say this the total amount of holes injecting into the base should be much higher than the electrons injection into emitter from base. Okay, then the, in terms of high current gain, the BJT device design is the right option. Okay, so second device, uh, let me dive into some more great details on how to understand the second device design guideline. So did you remember the equation for the saturation current in PN junction diode? So since we are talking about the emitter junction, which is one of the PN junction in BJT, so I naught saturation current can be written with this equation. So unit charge cross-sectional area of PN junction times Ni square, 10 to the 10 at room temperature divided by doping concentration and diffusion length diffusivity. Yeah, please go back to the ideal diode analysis again, then you're gonna find out this equation for saturation current. So this part and that part. So this first part indicates the whole current, and the second part indicates the electrons current. So in PN junction diode, once the hole has been injected into the inside, the hole can make its own hole current. Okay, all right. So herein, to increase this hole current much higher than the electron currents. Going back to the cross-sectional view gain of BJT diode, I'm talking about this hole current, right? And that is, electron current. So hole current should be much higher than the electron current in this emitter base junction. Okay. So for that purpose, how to design the emitter junction? Okay. Yeah, the answer is simply speaking, one-sided PN junction is necessary to achieve much higher hole current compared against the electron current. So the answer is one-sided PN junction. So if I write down a sentence to describe one-sided PN junction, yes, let's do that. The emitter side should be more heavily doped than the base. Okay, then we can achieve one-sided PN junction. But here in, I would like to give you a single note. once a p-type or n-type, whatever the type is, once the silicon semiconductor is much heavily doped, we should worry about this issue. What is it? Yes, notice that the band gap narrowing at very high doping levels. Since this band gap narrowing at very high doping levels increases what? Yes, Ni square value. You know, this N sub I indicates an intrinsic carrier concentration in pure silicon material. So we have used it as a kind of constant at room temperature, which was 10 to the 10 per cubic centimeter. But this N sub I, the reason why we can use it as a kind of constant is based on the constant band gap energy value, band gap value. But at very high doping concentration, the band gap has been decreased, so that N sub I value has been exponentially increasing. So we should worry about this value again when in the case of heavily doped side. Okay, so that one needs to be very careful not to dope the emitter too highly. Okay, too heavily. Okay, you can write it. So here again, the last notice message is, you should take into account the band gap narrowing event when you're estimating the whole current from emitter to base. And okay, this Ni value. If your doping concentration is very heavily doped, N sub I value is not anymore 10 to the 10. It should be increased a lot. Okay. And this part, the second part, indicates the electron concentration in emitter junction, and the goal of designing this high performance BJT device is to increase the Hall current than the electron current. So we should achieve much higher Hall current compared against the electron current. For that purpose, emitter side should be much heavily doped than the base regime. Then, in other words, simply speaking, one-sided PN junction is necessary to achieve this goal, which is the Hall current is much higher than electron current in forward biased emitter junction. Okay, so in summary, herein there are two major device design guidelines when it comes to achieving high current gain in BJT device. Okay, so we have learned the basics, how to define the current gain in terms of beta, output over input, so IC over IB. Okay, here's my pen. Yeah, think about the hearing, and I gave you two options in designing BJT device. Number one was the injected holes from emitter into base should not be recombined with the electrons in base. Okay, I mean, more specifically in the quasi-neutral base regime. So for that purpose, the quasi-neutral base regions, the total width of the quasi-neutral base should be much shorter than the magnetic carrier's diffusion length. You know what? At the end of ideal PN junction diode analysis, I have briefly went over, you know, the narrow base PN junction diode. At that time, I had give you kind of provide you with a small hint why we are using the word the base. Why is that? Yeah, why the base should be very narrow. Now you may get the answer for that question. Why the base regime should be very narrow? Why? Yes, we would like to have all the injected holes from emitter not to recombine with electrons in the base regime. Then we're gonna collect all the injected holes from emitter into base in the collector region. That then I sub C, collector current, is almost identical to the emitter current. Then the gain, high current gain, can be well implemented in BJT. So if your analog circuit designer would like to ask you, device engineer, to achieve high current gain, the number one device design guideline is to have your base regime very, very thin. Then you definitely implement very high current gain. And the second one for the BJT device design guideline was, emitter to base junction should be forward biased as well as one-sided doped. Then the Hall current is much, much higher than the electron current. Okay, so please remember those are two options in terms of BJT device design guideline. See you in the next movie clip. Bye bye.